Now to basically the last paper.
Yes.
I guess, Tarek, you will have to project your screen.
I'm here. Do you hear me?
Yes, just project
Good.
your screen, please.
Yeah, certainly.
High-performance computing engines for the FPGA-based simulation of the ULM. The paper is presented by Professor Tarek Ould-Bachir. Tarek Ould-Bachir is assistant professor with the Department of Computer and Software Engineering at Polytechnique Montreal. From 2007 to 2018, he was with Opal RT Technologies, holding various positions in the R&D department. From 2018 to 2020, he was a research associate with Polytechnique Montreal. His research interests include FPGA-based computing with applications to modeling and real-time simulation of power electronics and power systems. Please.
I'm sorry, I'm trying to share my screen. I don't, okay, I think here I have to. Do you see my screen now?
Not for the moment.
Not for the moment. I'm sorry for this.
You have a green button below. It says share screen.
Yeah, I saw the button, but it doesn't seem to.
And you have to
maybe
share
here.
the application,
Okay,
not do
and
like
then,
me that I projected my entire screen. Okay.
Okay. Do you see my screen now, or
now
at least the
good.
presentation?
Go ahead. Yes. Fantastic.
Okay, great. Okay, perfect. So good morning, everyone, or good afternoon, depending on the time zone. I'll be presenting a paper called High Performance Computing Engines for the FPGA-based simulation of the ULM. That is the universal line model that the last two presentations we're dealing with. This is the outline of the presentation. I'll briefly introduce the motivation and the problem I'm trying to solve. I'll present the mathematical foundation of the model, which was already discussed in the previous presentations. And then I'll go through the FPGA implementation of the line model, show some results, and draw conclusions and forecast future work. So regarding the introduction, the main motivation of this work is probably the hardware in the loop testing of traveling wave fault locators. So this is a new technology that is present on the market where relay manufacturers are able to locate a fault on a line independent of its length with an accuracy of a tower span, that is 300 meters. So you can have a line of, let's say, 500 kilometers, and if a fault arrives, then you can locate the fault and easily, I'm sorry, I don't know why it went to the next slide. You can locate the fault very accurately by observing the time arrival. I don't know if you see my mouse where I'm pointing to.
Yes.
Okay, very good. So this is TK1 and TM1. So if we compare the arrival time of the wavefront on both ends, we can determine the location of the fault. This is called the double-ended fault location. The other approach is to compare the time arrival on a single side and deduce the location. The accuracy is achieved by sampling the signals, the voltages and the currents at a 1 megahertz sampling rate. And when times come to test this kind of apparatus, there is no technology available. So there is an effort presently in real-time simulation to offer a real-time model for these relays. So here we see the relays from SEL, and this figure comes from another paper we published with the co-authors. And the purpose here is to emulate the simple grid on the simulator and feed the relays with real signals and test the algorithm. So this allows the manufacturers, I'm sorry, I don't know why it keeps moving from one slide to the other. So it allows a lot of flexibility in testing their algorithm and scenarios. However, the problem is that the simulation time step needs to be of 1 microsecond or less. Not only this, we have shown in the previous paper that the line model needs to be very accurate. It has to be traveling wave type line model, so no bisections. It has to be frequency dependent. Here we tested the constant parameter line, the CP, sometimes referred to as Bergeron line, and we demonstrated that false peaks here are observed. So the double-ended fault location was correct, However, the single-ended was unfeasible because of these false transients here. So what we are trying to do here is to implement the ULM on FPGA. The ULM is very computing hungry. And what we want to do is to achieve a time step of 1 microsecond. So I'll briefly go through the mathematical formulation of the model. It has been presented previously. So we have a multi-conductor line here. It can be a cable, it can be a line, an aerial line. And we have the current at the terminal. We have the incident and the reflected current. And this line here will be replaced by 2 Norton equivalents, one at each terminal. We have a characteristic admittance matrix that is lumped. And then we have a propagation function that will read the current on the other terminal and will reflect it. And it will apply a delay. Usually these matrices are fitted and are given in the frequency domain. And when we want a time domain solution, a state space approach is used. Here you see the equations. So we have multiple states called here x, y, and xh for the propagation. And we see that on the propagation function side, we have these delays that are grouped as the previous presentation mentioned. At the end, we have a history current that is injected in the Norton equivalent, and this one is obtained from the sum of these 2 terms. I'm sorry for this. So we see that a lot of computation is needed for each single time step. Let's see how we can implement this on FPGA. I'll start with an overview of the algorithm and the hardware computing engine. So the audience needs to understand that here everything is done in parallel. So whenever we see a block, there is actually a application-specific processor that handles the computation. Like here, we have a nodal solver. So this nodal solver will take all the independent sources that can be voltage or current sources and will produce some outputs, as well as the reflected currents at the line terminals and the voltages. These values, here we see a vector, are fed to n instances of what I call ULM computing engine. That is a computing engine dedicated to simulate one line. So we compute the reflected current and the voltages, we feed them to these engines, and these will send us the shunt history current and the incident current that will be fed into a buffer. So the algorithm reads like follows. We compute the reflected and the terminal voltage here. This is sent to update the buffer here for the propagation function and used to compute the history shunt and the incident current for the next time point. So there is like an anticipation, and we can then move for the next time point of the simulation. Each computing engine is comprised of 2 modules, one for the YC function and the second one for the H function. If we start with the first one, the model for the YC, this is quite straightforward. So we have multiple state space that need to be computed. We do that serially. So we take one state variable at a time and we update it. This is the block diagram of it. And once we're done with this, we sum all these states to produce the shunt history current. We can manipulate, we can move the blocks around to make it faster, to reduce the latency. And this is done by putting in parallel this block here and this one. Basically, it's just the sum of the 2. So we update the terms, and once we're done with that, we feed it to a reduction unit. And what is mentioned here in red, FDP SAF, this stands for Fused Data Path Self-Alignment Format. So this is a technology or a method that I have proposed many years ago to produce custom-made floating point cores on FPGA that are characterized with very low latency. So basically in hardware, floating point and fixed point are the 2 approaches to computations on FPGA. and floating point is the preferred one when we do scientific computations. However, it has a hardware cost and it's characterized by a very high latency. By using this approach, by fusing the data path, that means that by fusing the multiplication and the addition and using this self-alignment format, we can have modules that multiply and add very efficiently and that exhibit very low latency. So for the YC model, this is very easy to implement. For the H model, it's a bit more complicated. One of the reasons is that because usually the H model will imply more computations. Here is a reminder for the equation. We see that we have a delay here that is not necessarily an integral multiple of the time step. So if this equation here shows two terms, actually we'll be reading three values. The H model here, will read data from a buffer. So we'll be reading three values at a time, and then we'll multiply by this beta, and then we'll update the state. So how can we improve this computation? First, we need to understand that here we cannot put this MVM and the state update in parallel because of the interpolation that needs to be done. So what we do here is we put them serially. And then what we observe is, since there is a buffer here, maybe we could take the buffer and put it at the end. If we do so, what will happen is we'll be able to read one sample whenever it is needed. This is what is shown here. I'll go back to the previous slide. So I'll compute the value that is needed and I'll put it in the memory, and that one will be read whenever needed. So if I go to the next slide, what we see here is we have the nodal solver that computes the Y, the V, and the incident current. And once these are available, the YC module and the H module will start their computation. So if we simply implement as the equations are written, and we'll see that these are the latencies, and the latency of the line will be the maximum value of the two latencies. So this is shown here. This is illustrated. We suppose that the shunt history current will be available before the incident current. However, this value here can be computed beforehand and made available as soon as the values are fed by the nodal solver. So we suppose we have these voltage and incident current arriving, and we provide the solver with the next value it needs. However, I'm going back to the previous slide. However, we cannot just use an output buffer because these delays are different depending on the mode that is being considered. So we need an input buffer that is not too large, quite small, like maybe 50, with 50 samples, that will be just to accommodate for the difference between the maximal delay and the minimal delay, and then we'll handle all the samples in an output buffer. So by doing so, we considerably reduce the latency, and we can have a model that is very efficient. So now I'll move to the results. I have two test cases. The first one was just to assess the accuracy of the implementation. So what we did is we had a three-phase line, and we apply the fold on phase A. And here we see the simulation. So this is for 0.25 second. And at 0.1 second, we apply the fold, and the fold is cleared after 0.1 second. So the total duration here is 0.1. And what we see is that our result from the FPGA match the results from EMTP. So the model is very accurate. The second test case that is considered here is the traveling wave fault location. So we suppose that there is a phase to ground fault at 20 kilometers from terminal K. And we're reading and filtering and generating the traveling wave currents on terminal K and terminal M. And these are the observation. What we see is that the time duration between the two peaks, so between the peak at terminal K and the peak at terminal M, is 202 microseconds. And this translates, so there is an equation that translates time into distance, and this translates to 20.003 kilometers. So the accuracy is 3 meters in this case. Then we consider the 2 peaks that we see here. So the time duration here is 135 microseconds. So what we have demonstrated here is that using this model, we can have an accuracy of less than 300 meters. Presently, in this case, it is 47 meters from the single-ended configuration. This hasn't been achieved in the literature. Finally, if we look at the FPGA implementation, what we have few metrics that we would like to present. The first one is that the clock frequency of the FPGA is quite high. So on FPGA, usually people can implement solvers with the clock frequency of 100, maybe 150 megahertz. This implementation here, because of the fused path SAF methodology, achieves 250 megahertz. So this is very effective. The shortest latency that we can achieve using this model is 200 nanoseconds. This is more or less 50 clock cycles. This is very important because in this case, what we were trying to do is simply implement the model for real-time applications, but other applications can be considered. And for that case, it can be very important to be able to feed the solver, the computing engine, with new data to process in a pipeline fashion. So we could process a new line every 200 nanoseconds. This can be very interesting if we target the acceleration of EMT programs. This is one of the aims of this work. However, it hasn't been tested in this paper. We also see that the memory, so when we do design on FPGA, we have what we call block RAMs. These are small memories that are available on the chip. So the access is very fast, and we see that it is not a limiting factor. We only used, for the second test case, only 16%. And it wasn't a very big FPGA. So with larger FPGA, with better memory resources, we could do certainly more complex setups. The main limiting factor here was DSP. We see that for the second test case, we use almost everything. However, this FPGA is dated. It's from 2010, I believe, and new technology provides many folds more DSPs. DSPs are blocks dedicated to do some computations, typically multiplication. So what this shows is probably one of the future avenues that should be taken is to share the computing models for multiple lines. And this is one of our conclusions. So the conclusions, we show that we were able to implement the universal line model very efficiently with a latency of 200 nanoseconds. Although the example shown here used a time step of 1 micro, because otherwise the number of samples would be too large, but not really necessary for the application. We combined a scheduling that was appropriate for the application, as well as custom floating point operators to achieve low latency. And what we have showed is that we are able to test a traveling wave application for double-ended as well as single-ended configurations. Finally, for future work, what we plan to do is to consider larger networks. So this was a very simple test case. We plan to implement computing engines that have hardware reuse, that is, the same model is being used for multiple lines. And finally, we'd like to implement these models for the purpose of the hardware acceleration of EMT programs. So thank you for your attention. And that's going to be all for me. Thank you.
Thank you very much for this presentation. We have one question from Professor Fu. It's about the nodal solver on FPGA for simulation of distribution networks.
Yes.
Is pre-computing inverse mana matrices for all possible switch combinations still the best option?
I believe it is the best option. The other option is to use Pejovic model for the switches. However, these tend to introduce false transient. In this paper, we use the mana with the resistive switch. So whenever we have a fault, we simply replace, we put basically a small resistance to from phase to the ground. So we had only one switch. It was very easy to handle. In this case here, we used, so this is another paper. I have the reference here. So that was another paper. In that one, we used Pejovic. And in that case, we can handle more switches. However, it was very tricky to set a proper value for the conductance of the Pejovic switch in order not to alter these signals here. So to get the best accuracy, the resistive switch model is the best approach.
Okay, any other question? I do not see any questions in the Q&A. Any other question from the audience? Since there are no more questions, I think we are right on time. It's already 9:41. So we can now conclude this session. Thank you very much for all these excellent presentations. I don't think there is anything more to say. So thank you very much. Also to Andre for helping us with the system. So we are getting more and more experience with this kind of stuff now. So thank you. Have a nice day to everybody. Bye-bye.